Today we're going to study section 5.4, which contains something that hopefully will blow your mind. It's one of my favorite sections again. So we're going to start with an example that shows part of what we're going to do in that section, and I find it quite amazing. In 6th grade is probably the first time students study equations, one-step equations like x plus 3 equals 5, or 3x equals 12, and so on. A little bit later, in 8th grade, students start looking at systems of equations. Here's a simple system of equations. So when we look at it, we probably can figure out that the solution is x equals 2 and y equals 3. Let's look at another system of equations. The first two are the same, and there's just a third equation here, but let's look at it separately from what we saw above. This is a system of 3 equations and 2 unknowns. If you try, you're probably going to try x equals 2, y equals 3 to see if it fits in the third equation, and you'll notice that it doesn't. 2x plus y is not equal to 10. So we would typically say that there's no solution to that system of equations. And that's what we're going to break today. We're going to look a little bit beyond that. Because that's true, there's no solution. However, if we look at some values of x and y, some of them are better than others. Some of them, if I plug in x and y, are going to give me values that are quite close to 5, 8, and 10, and others not. For example, if I pick x equals 3, y equals 2, and I plug it in the left-hand side of each equation, I get x plus y equals 5, x plus 2y equals 7, and 2x plus y equals 8. If on the other hand I try with x equals 4 and y equals negative 1, the right-hand side comes out as 3, 2, 7. So our system of equation was trying to get x plus y equals 5, x plus 2y equals 8, 2x plus y equals 10. Now we know it's not possible. But if I look at these two results I have here, I think everybody would agree that 5, 7, 8 is better, if you compare it to 5, 8, 10, than 3, 2, 7. So even though there's no solution to our system of equations, we can look at numbers for x and y and decide that x equals 3 and y equals 2 is a better option than x equals 4, y equals negative 1. After all, in the real world, rarely are things perfect, rarely are solutions exact, and so maybe we want to start looking at imperfect solutions that are as good as we can get. And that's what I think is really, really new with equations. Until now, either it had a solution and we knew it, or knew the solutions with an S, or there was no solution, and that was it. Now we're going to look at imperfect solutions, but among them, which one is the best? So here now, enter linear algebra. This is how we write this system of equations with matrices and vectors. X plus y equals 5, x plus 2y equals 8, 2x plus y equals 10. So it's time to review a little bit what this means, and this is going to remind us of a lot of things we've done in the previous chapters. What do these parts mean? Well, first of all, xy, that's a vector. It's a vector in 2D, so here I represented a random vector in blue to show it, but this xy, since we haven't chosen x and y, could be anywhere in the plane. Secondly, we have a matrix. The matrix 1, 1, 2, 1, 2, 1 performs a transformation. So every matrix performs a linear transformation, and vice versa. Every linear transformation can be expressed with a matrix. What kind of transformation does it do? Well, we know something about this transformation. First of all, we know that the output is going to be in 3D. You can convince yourself of that by just trying to multiply the matrix with x and y, the vector xy, and you'll see that you get 3 rows in the output, so you get a vector in 3 dimensions. But we know more. We know that the columns of the matrix span the image. So here are vectors 1, 1, 2 and 1, 2, 1. And any linear combination, when we multiply the matrix with x and y, we get every linear combination of these two vectors. is going to span a plane in 3D. So there might be a little bit of a perspective issue here. You may wonder, what does this plane look like? Don't worry about that. What you need to be aware of is that the two orange vectors, which are the column vectors of matrix A, span the image of T, and that's a plane. So what about the right-hand side of our equation, vector 5, 8, 10? Well, here it is, and no wonder we can't find a solution, because this green vector 5, 8, 10 isn't in the plane. So we can try anything we want with x and y. We're never going to reach the green vector because it sticks out of the plane. So I removed a few things, and now we continue just with this abstract idea of having a plane, which is the image of the linear transformation, and a green vector that is going out of the plane. By the way, 5, 8, 10, it's not to scale, but just remember that this green vector is out of the plane. What we can do is think of the projection of this green vector. Here is the projection. Now, I know that we often use an image for the projection. We say that it's the shadow of the green vector if the sun was perpendicular to the plane. I want to offer now a new image for what projections are. To do that, imagine that the green vector is fixed and it has a magnet at its tip. Imagine that the red vector is not fixed. It can travel anywhere in the orange plane. However, there's also a magnet that's going to be attracted to the green magnet. So naturally, if the tip of the red vector is far away, it will come where we see it here. Where will it stop? It will stop at the position of the projection of the green vector onto the plane. This second image is interesting because it kind of reverses the way we think about projection. When we think of the shadow image, we start with the green vector and then we cast a shadow and we get to the red vector. When we think of the magnet, it's more like we're starting with the red vector, and this red vector is anywhere in the plane. Of course, it's fixed at the origin, but the tip of the vector is anywhere, and then it gets magnetized and it approaches here. And so it looks like it's more red going to green with the magnet rather than green going to red with the shadow image. This is going to be closer to what we're going to do today. In terms of math, what we'll see when we do the notes is that to find the red vector, we're going to actually look at the blue vector and find that this is the shortest distance between the two tips of the vectors. If red was anywhere else, then this light blue vector would have a greater magnitude. In terms of our original problem, when we were trying to find the best solution for the system of equations, we can now say that the red vector is the best solution. We will never be able to find x and y that go to 5, 8, 10, but we can find x and y that go to the red vector. In terms of what we will do in the notes, the x and y values that are the best for the system of equations is going to be written a vector x star, and the components of vector x star are x star, y star. In the notes, we'll see that we have to check that the matrix A has a kernel of 0 before we can proceed. And the formula that we'll discover is that to find vector x star, we have to apply this equation. If we do that, we can totally do it by hand. There's no problem. We find that the solution is 3.909, approximately 1.909. So x star, again, is the best solution given that we cannot find a perfect solution. And vector x star in purple is transformed to the red vector, which is the closest to the actual values that we could not reach. So remember, x plus y equals 5, x plus 2y equals 8, 2x plus y equals 10 is the system of equations we were trying to solve. If we try with x star and y star that we found, here is the solution, and we can compare 5.8 instead of 5, 7.7 instead of 8, 9.7 instead of 10. That's the best we can do. And I think that's really really amazing that we can suddenly think a little bit differently than just, oh, there's no solution, end of story. Now, if we look at the solution, 5.8, 7.7, 9.7, it's quite close to 5, 8, 10. This is great, but it's not always going to be the case, of course. If the green vector was very long and almost perpendicular to the orange plane, or literally perpendicular, then there would be, even the best solution would be terrible. But that's not the point. That's not where math fails. Math is just giving us the best possible solution among all the imperfect solutions. So one application that you are probably totally aware of without knowing that it was done like that is the line of best fit. When you have a cloud of points in statistics and you're trying to place a line of best fit, this is what you do. You're trying to solve a system of equation that has no solution because there's no line that goes through 25 points that are spread out all over, but you can find the best line that goes as close as possible to all of the points. And we will do that in the notes as well with something even more impressive than a line of best fit. We'll do it with a parabola of best fit. So, on to the notes now. So, in section 5.4, we will start by seeing a formula that states that the orthogonal space to the image of A is equal to the kernel of the transpose of A. And then we'll discuss the projection as the vector closest to X in the subspace. And finally, we'll apply what we've shown to define the least squares solution of a linear system, which is what we did in the example earlier. So firstly, we have the theorem, which is the same as the formula here. And how do we define that? It might be really hard to understand what this says, but the proof is surprisingly easy. If we define matrix A using column vectors, so we focus on the columns of A, the image of A is the span of those columns. So that's already a good sign. And now we're wondering, what is the subspace orthogonal to that? Well, it's made of vector x's such that v1.x, v2.x, v3.x, etc., vn.x equals 0. This is the definition of the orthogonal subspace. But how can we write that? Well, it's actually not very hard. We can write it in one equation, one matrix equation, and this in one equation represents what I just said now. It's v1.x equals 0, then v2.x equals 0, etc., all the way to vn.x equals 0. I said dot, but really it's a multiplication here. Now when we look at that, we have actually the transpose of A. Instead of having column vectors like in A above, it's now row vectors. It's the same vectors, but the columns became row, so that's the transpose of A. And if we observe this matrix equation, what are the type of x's that are going to belong to that? What are the type of x's that are going to satisfy this equation? All the x's that are in the kernel of the transpose of A. Let's have a look at an example. If you consider the line defined as the image of 1, 2, 3, let's use the theorem to find what the orthogonal subspace to V is. This looks like a vector, but let's think of it as a matrix, a 3 by 1 matrix. What kind of vectors comes after that? If we want, let's call this matrix A. If we want to do A times X, what kind of vector X do we need? We need a one-dimensional vector. So it's going to be 1 times X, 2 times X, and then 3 times X. So the image is, in fact, any multiple of the vector 1, 2, 3. Here, k times 1, 2, 3. That's the output if my vector x is just a number k. Then, using the theorem, we know that the orthogonal subspace to V, which is the orthogonal subspace to the image of 1, 2, 3, is the kernel of the transpose of A. So now we have 1, 2, 3 written in one row. This time, if we wanted to place a vector after this matrix 1, 2, 3 in a row, it would be a three-dimensional vector like that, 1, 2, 3 times x, y, z. What's the kernel of that? It's when 1, 2, 3 times x, y, z equals 0, and if we proceed to multiply these two matrices, we get x plus 2y plus 3z equals 0, and that's exactly the equation of a plane as we remember from multivariable. So indeed, as we would have supposed, the subspace that is orthogonal to a line is the plane perpendicular to that line. We are not going to prove the next two theorems. For an n by m matrix A, the kernel of A is equal to the kernel of the transpose of A times A. And then, even more important, but it proceeds from that, if a matrix A is n by m, and if the kernel is 0, then AT times A is invertible. So what's interesting here is that matrix A is not necessarily a square matrix. It's not necessarily n by n, it's n by m. But when we do AT times A, it always becomes a square matrix, and that square matrix is invertible. So A is not invertible, but AT times A always becomes invertible, provided the kernel is 0. Now what we've discussed in the introduction problem was how to define the orthogonal projection differently from thinking about it as a shadow, but more with the magnets. The projection is the vector, projection V, such that the vector here in blue is the shortest among all possible vectors in the subspace V. In Nick O's drawing here, we can see that the blue vector is shorter than the purple vector here. So we will define the projection of a vector B as the black vector such that when we look at the connection between the tips, it is as short as possible. So the application is what we've seen in the introduction problem, that when we have an inconsistent system of equations, we can find the best of the non-perfect solutions, and this is what we call the least squares solution. So the theorem we have here is the first and major big step to getting to the formula to find the projection. So if we define AX stars as the least square solution, it's the best solution we can get, then the blue vector B minus AX star is in the orthogonal subspace. It's therefore orthogonal to the image of A. The image of A is this plane, AX star is in the plane, and then B minus AX star is in the orthogonal subspace. So we can apply the theorem from above. If B minus AX star is in the image of A orthogonal, then it means that B minus AX star is in the kernel of A transpose, not the kernel of the image of A transpose. All that means is that if we do AT times B minus AX star, we will get 0 because B minus AX star is in the kernel. So by distributing, we get AT times B minus ATA times X star equals 0. And if we move one of these parts to the right, we reach the equation here. We are very, very close, of course, to solving for X star, and it happens here. So there is a requirement. If you want to get X star, you need the kernel of A to be 0. If the kernel of A is 0, then ATA has an inverse. Just a comment about here, why don't we distribute this power of -1 to AT times A? Well, as we saw, A is not necessarily a square matrix, so A might not be invertible, but AT times A is always invertible. So an example here that I'm not going to go into many details because we've seen it. We've seen a more detailed example that carries exactly the same information. To find the least squares solution, you apply the formula that was just above. So in this case, this is it. And just as you copy, realize that here, this is not 8, 6, it's 0, 0, 6. So how close is the projection A x star to 0, 0, 6? And we notice that it's negative 1, 2, 5, so not very close, but it's still the closest. Okay, so that gives us a method to find the orthogonal projection onto a vector, onto a subspace V as well. Since we know that the projection of any vector B is AX star, we can just substitute what we know X star to be, and we get a projection matrix, which is A times AT times A inverse times AT. This will give us the matrix of the orthogonal projection onto a subspace. So we've done that now 3 times. We did it in 5.1, we did it in 5.3, and we're doing it again in 5.4. What was great in 5.3 compared to 5.1 was that we had a matrix to find the projection of a vector onto a subspace. That was wonderful. What's even better here is that we don't even need an orthogonal matrix. We don't need an orthonormal basis. We can use any matrix A and just do that. So this formula is bigger, longer than the formula we had in section 5.3 to find the orthogonal projection, but this one is far more general. You can apply it whatever matrix A you have. Example, what is the projection from R4 onto a subspace spanned by 2 vectors? So we are in 4 dimensions and we are projecting perpendicularly into a plane, and here is the result. If you go back to 5.3 and you use the example in 5.3 and use this formula instead of the formula for 5.3, obviously you will get the same answer. This one is more general, but it includes the case from section 5.3. Finally, least square regression. Fit a quadratic function to the 4 data points, negative 1, 8, 0, 8, 1, 4, and 2, 16. I sketched the points here. So clearly we know that it's not possible to have a parabola go through these 4 points. It's visibly impossible. But what is the best parabola? Shown here in purple. How can we find the equation of this parabola? We are going to set a system of equations, since we are looking for a parabola f of x equals ax squared plus bx plus c. We can plug in each point and it gives us a system of 4 equations and 3 unknowns a, b, c, which we can write as a matrix equation and then just apply the formula from above, or like we did in the introduction example, and we get a equals 3, b equals negative 1, c equals 5. So the parabola of best fit is 3x squared minus x plus 5, shown right here. So that's it for this section full of interesting stuff. So thank you for listening.